So section 3.5 deals with rational functions. Some of you may remember that rational functions are functions that have variables in the denominator. So we've talked a little bit about them. We've talked about their restrictions. We've solved some rational equations. We have talked about them a little so far. We've even talked about finding the domain and range of them, right? But what we haven't talked about is what their graphs look like. And that's what this section is going to be, to help you understand when you have y equals a rational function, what those graphs look like. Also, what those restrictions show up as on a graph. And they can show up actually as a couple of things. So we're going to start talking about that. A rational function is just any function that has variables in the denominator. This is how your book defines it. It's not really all that necessary. You just need to know it's any function with variables in the denominator. And as with any function with variables in the denominator, there is a chance that you will have restricted x values. And those restricted x values affect the domain of the function, and they affect the graph of the function. So just for a recap for the first example, because some of you didn't do so well on the quiz on this section, back in 3.1 where we did domain? Yes. Back on that quiz from 3.1, we had a lot of wrong answers in those first couple of questions. So we want to make sure that we understand domain fully before we actually get into graphing. So if we take this one, y equals 3x plus 2 divided by x squared minus 7x plus 12, and we want to talk about its domain. That means I first need to find all of its restrictions. So what we're going to do is keep the top. Now, if the top would factor, I would recommend going ahead and factoring it, but it won't. So we'll keep the top, and we're going to go ahead and we're going to factor the bottom. The bottom will factor into x and x, both minuses. And what multiplies to positive 12 but adds to negative 7?
3 and 4.
Okay, so negative 3, negative 4. Y'all understand to there? Name the two restrictions. We know that x cannot be 3 and 4. We have no idea what that's happening on the graph yet, but we know that's what x cannot be. And soon we're going to understand what they are on the graph. If I want to list the domain then, I have to list every number except for 3 and except for 4. So if you think of it from a number line, those are the only two numbers that aren't allowed. Everything else is good to go. X can be anything for this function. It just can't be positive 3 and positive 4. So that's going to break into how many intervals? 3 separate intervals. So let's write that down. Negative infinity up to 3, but because it can't be 3, we put a parenthesis there. Unioned with 3 to 4, and again from 4 to infinity. And they'll all have parentheses. That's how you find the domain of a rational function. So for those of you who missed that, you might want to go back. That was, I think, the first one on your quiz. It's different when you're taking the domain of square root functions, and some of you need to review that as well. It's totally different for square root functions. So make sure you go back and look at that. But those are for rational functions. That brings us up to what do these graphs look like? Most restrictions for a rational function show up on the graph as vertical asymptotes. I don't know if this is a word you've ever heard, okay? But an asymptote is when a graph approaches a line as shown in this figure. If you trace this graph kind of from the right, this way, do you see how it's hugging the y-axis there? It's getting close to the y-axis, but it's never actually equaling the y-axis. That y-axis there is functioning as what we call a vertical asymptote right here. And that's what we're going to talk about first. But as it turns out, this particular graph also has a horizontal asymptote this way. So as we trace from here out to here, see how this graph is getting closer and closer to the x-axis but not actually crossing over it? Yes? that is called a horizontal asymptote. And rational functions can have either one, and they can have both. They don't have to have either, but they can have either one or both. There also is a third type of asymptote called a slant asymptote. We're not going to talk about that until a little later on, but they are there. So the goal of this section, okay, is first off, we want to understand when a graph has an asymptote, when it doesn't. So you need to be able to look at a function and tell what are its vertical asymptotes, what are its horizontal asymptotes, does it have slant asymptotes? If so, where are they? How do we find them? That's our first big endeavor. We have to figure out those three things. That's where we're headed, okay? Then you need to figure out, once you know those things, how do I get it on a graph and figure out what it looks like, aside from using my graphing calculator. So that's where we're headed. So what's an asymptote? An asymptote is an invisible line. An invisible line that a graph approaches, but usually doesn't ever actually equal. Make sense? Yes?
Yes.
All right. You may not like it, but that's what it is. Do you need a minute to take notes here, or are you ready to flip the slide? You ready? Okay. The first thing I'm going to teach you is how to find vertical asymptotes. I wish your book started with horizontal, but they don't. And they honestly put a lot more emphasis on vertical asymptotes. So we'll start there. But it's actually quicker to find horizontal first. So once we get there and we talk about it, I'll recommend that you find horizontal, then vertical. But for now, we're just going to talk about vertical asymptotes. Are y'all ready? To find vertical asymptotes, start out like you're trying to find the restrictions. Go ahead and factor the top and the bottom. So go ahead and factor the top and the bottom if you can. So it's a lot like finding restrictions. So here's example 1, or example 2a. See how that factors? What are the two restrictions? Negative 4 and positive 4. What variable? Is it y or x that's restricted?
X.
It's x. That produces vertical asymptotes at the two lines x equals negative 4 and x equals positive 4. There are two vertical asymptotes in this graph. The two restrictions in this graph are acting as vertical asymptotes. So where the denominator goes to 0 is a restriction. And most of the time it is also called a vertical asymptote. There is one time that it isn't. I'm going to show it to you in example, in part B here of this example. And guys, we'll stop after this example for the day, okay? We just get you through vertical asymptotes. Are y'all good? Okay. So for the second part, we have g of x equals x minus 4 over x squared minus 16. So we're going to start out the same way. We're going to factor the top and bottom. The top won't factor, so we're going to keep the top. The bottom will factor into x plus 4, x minus 4. What do you notice about this one that was different from part A? There's a binomial on top that cancels with one of the binomials on bottom. Okay. So go ahead and cancel it. Okay. Do you see that what's left over is 1 over x plus 4? Now, just to be clear here, positive 4 is still a restriction, but it is not a vertical asymptote. Only restrictions that do not cancel produce vertical asymptotes. Y'all understand that? Okay. So the only vertical asymptote here, can I abbreviate it VA? The only one is x equals negative 4. And I'm not sure that your book points this out. The restriction that cancels is called a hole in the graph. And I do want you guys to know it. There is a hole at positive 4. Do you understand that? Positive 4 over here. Do you see that? Canceled out. It didn't make an asymptote, but it's still a restriction. Positive 4 is a restriction. But when a restriction cancels, it produces a hole. At that value, comma, whatever the y value is if you plug that number into the reduced function. Look at the reduced function. See right here, this is the reduced function. Plug the restriction into that function, and what do you get? You get 1/8. Okay? That's where the hole sits. And I will show you these when we graph. So you're not going to know what to do with it yet, but there is actually a hole in the graph. I don't know if you've ever seen one. We talked a little about them. You have something like this. There's a hole in the graph right there. That's what it looks like. The value of that hole is found the way we just found it in this particular example. Isn't that neat?
What did you do?
If you're not amused, hold on guys, we got one more to get through. Does everybody understand? If the restriction doesn't cancel, what does it make?
Asymptote.
A vertical asymptote. If it does cancel, what does it make?
Hole.
A hole. How do you find the y value of the hole?
Plug the one that's the hole back into the
You plug the
reduced.
x value of the hole into the reduced function, and that finds the y value of the hole. Asymptotes are a lot better than holes. Do you understand? They're much easier to find. Look at part C and tell me where its vertical asymptotes are. Well, first off, does it factor? No, it doesn't factor. So nothing's going to cancel. So does not factor, does not cancel, so there are no holes. Do you understand that? The question is, are there asymptotes? Well, to find out, you set the denominator equal to 0 after you factored and canceled. If it didn't, take the original denominator, set it equal to 0. Try to solve it, and what happens?
You get imaginary.
You get an imaginary number. And we do not, you get 2 of them actually. We do not list imaginary asymptotes or imaginary holes. So we say it has none. Uh-oh, I can't spell today. That's how you find vertical asymptotes and holes. And sometimes it doesn't have a vertical asymptote or a hole. And you need to recognize when those three things occur. We'll stop there.